So Jason and I have known each other about 20 years, over 20 years.
Yep.
I think, yeah. So maybe, well, you probably read the blog posts because you registered. But Jason and I did a couple of CRCs together, so he's got another title I like to call him the Grand Poobah of the CRC. We have another one coming up in
2026. No, 2029. In 3 years we'll have it.
Okay. All right. So look to be nominated for some
absolutely
volunteer work
we will
Jason,
volunteers
just by participating in this class today. Yeah. So we last year we did a basics class just on electrical for dummies. And someone from Ring and Deuce, I think it was Kurt, suggested, what about psychometrics? And I was like, all right, let's see if there's any pull there. And this is our highest registered, highest attended class so far. So it's becoming readily apparent to me that people aren't as interested in all the subtle nuances of this and that. I think we need to get back to a little bit more basics. So conveniently for us, Jason volunteered to do this class. He's an excellent teacher with a wide-ranging past. So if you haven't read Jason's past in the blog, it's pretty worthwhile. So prepare to be entertained with our psychedelics / psychrometrics class. We're going to try to weave as much stuff as, well, not we, Jason did the whole thing. We're going to weave as much fun into it as we can. And otherwise, it might be a dry and over wet subject. Oh, that's so bad. So bad.
I'll try to make it as formally informal as I can.
All right. So thanks for coming here, and thanks to everybody who's on their webinar. And all right, enjoy.
All right.
Thanks, Jason.
Appreciate that
How
time.
about a nice hand for our speaker?
So Jason Leffingwell, I work at Grumman Butkus Associates in Wauwatosa, consulting engineer, HVAC energy-related items. Do a lot of work in big pharma, dealing with dust collection, pressurizations for containment spaces. So I will say, I was asked to present on psychometrics, and I asked Tom what he wanted me to cover. I'm by no means an expert, but I certainly enjoyed the topic of the matter, and I've dealt with it for a number of years. So after I signed on and agreed to it, I went and looked at the sign up online, and it was psychedelic psychometrics for dummies, and I was like, how fitting. So I'm going to try to make this a light subject, but it's very informative, but it will be informal in the process. So any questions as we go along the way, please let me know. But I have, sure, absolutely. So what I'm going to do is kind of just walk us through some simple approaches to utilizing the psychometric chart and what psychometrics are. With that, I think we'll get started. I will say a lot of unfamiliar faces here. That's awesome. So thank you for attending, as well as the folks online. This is the largest presentation that I've probably given in my day. I've presented a lot to smaller groups, so pardon me if I do stumble. I don't think that I will, but I guess let's just make light of it and have some fun with psychometrics.
If you stumble, we will be making fun of you.
That's okay. That's okay. I have been made fun of before in my day. So a little bit of an agenda of what we're going to talk about. We're going to look at some fundamentals of psychometrics. What I call the holy grail of air properties. We'll dive into some processes as we, so that the psychometric charts are intended to be utilized as we go through. So I've kind of built this to where it can be interactive and you can follow along. So it'll be a hands-on experience in that regard. Pardon all the folks online. If you do have a psychometric chart PDF or on hand, please participate. We'll go through a little bit of a space analysis, looking at an air system, and then a couple final tips that I've got. You'll see some random artwork as we go through. That's intended to go along with the psychedelic side, and that's all from an artist's name was Alex Gray. He's more transcendental, psychedelic type artwork. Yeah, I think it's pretty fun. You'll get it. I think you'll like it. So with that, we'll dive into some fundamentals. So psychometrics was originally put together by Mr. Carrier. We all know who Carrier is, right? The manufacturer. Well, Mr. Carrier himself, back in the early 1900s, he created he found the relationships of air properties, and he overlaid these onto what we call the psychometric chart. That was the first of its kind. In my mind, as an engineer, I'm always fascinated to see what knowledge or what the founders of like math and the sciences of all the work that these guys and gals did 100, 200 years ago to really allow us to do what we do today, and to be able to overlay all this onto a chart. I think it's absolutely mind-blowing to make those connections of all those relationships. So what can we do with this psychometric chart? Well, it allows us to predict the changes in the built environment as we add heat, remove heat, add moisture, remove moisture. We can utilize this to find new state point properties. So with that, the psychedelic side of things, early 1940s, late 1930s, Mr. Hoffman, he was a chemist for Sandoz Laboratories in Europe. He stumbled across what is dubbed LSD. So this was a lot prominent in the 60s. He stumbled upon this by looking for a way to not stimulate the respiratory and circulatory systems for the uterus. He was trying to find a way that was safe to be administered. It got put on a jar, left on a shelf for about 5 years after he had discovered it. He then, one day, 5, 6 years later, 1943 I have here, he took a small dose of that, 25 milligrams, which became known as LSD 25 in the 60s. So that first concentration he took by himself. He kind of, as any scientist, he jotted down what the experiences, right, what he felt. So with that, 3 days later, with a colleague, he decided to administer a larger dose to himself. 250 milligrams, thought would be a safe concentration. Well, that ended up being a lot. And so he hallucinated. He was seeing things that you wouldn't in a normal day, everyday life. So that was documented with his colleague. He then chose to ride his bicycle home from work that day, which has now been dubbed, Tom, you're pretty almost spot on, April 19th. We're almost there, but it's called Bicycle Day. So that's in celebration of Mr. Albert Hoffman for all those in the psychedelic world. And this is another Alex Gray of piece of artwork for Mr. Hoffman. My friend's band, the Grasshoppers, had a song called Uncle Albert. They wrote for him, so it goes back a little bit of my history there. But Bicycle Day is right around the corner. So psychometrics, psychedelics, there are some common grounds, right? They deal with altered states. One air, one consciousness, almost 200 years of combined knowledge in the fields, which is pretty impressive if you think about it. And they're both what I would say esoteric, understood by very few and known by even fewer, right? So there's not you talk psychometrics to anybody in the non-HVAC world, they look at you like, what? You know, you could talk about dew point, you could talk about all these things, and they're going to look at you with a glazed look over your eyes. Same thing with psychedelics. People are going to look at you with a glazed look over their eyes. So, two worlds colliding, and I was struggling in my mind how I would present two things like this. So, bear with me. It's, I think we'll make light of it. So, atmospheric air. What is it? We all know that air has got a bunch of gases comprised of it. We've got oxygen, nitrogen, argon, carbon dioxide at varying concentrations and volume. So when we look at this back in the 50s is when we had to standardize this. Where do we start from? Right. So we came up with a point that I'm jumping ahead of myself, but when we look at the dry air, right, what's in our air, we got 78% nitrogen, we got 21% oxygen, and a little bit of other gases that are mixed in there, right? And so with that, there are contaminants, there's water vapor, except the water vapor has been completely, that's out of it, but when we add moisture, we change that state, right, of the air. So it's a combination of the dry air and the water vapor. So our good friends at ASHRAE, ASHRAE I'm a huge proponent for, as Tom had said. They've got a lot of information on on this topic, so at the end of it all, check it out. But the folks at ASHRAE, again, a bunch of smart people, they had to start to hone in on what's standard. How do we set it up so that across the board we can be on an even playing field, right? So apples to apples, not apples to oranges. So they started setting some of these constants. We got the acceleration of gravity. We got air temperature at sea level is 59 degrees. What's at pressure is almost 30 inches of mercury. And that dry air, that dry atmospheric air, we're assuming acts as a perfect gas. There's an assumption in there, right? But it's not always perfect, but we're assuming that it is, so that we can do what we've got to do when we analyze things psychometrically. So they set this standard atmospheric temperature and pressure to be 70 degrees Fahrenheit at almost 14.7 pounds per square inch. So that is getting us to nearly that 30 inches of mercury as they set back here earlier as we discussed. So this is a standard. When we start talking about some simplified formulas, it's based on this standard point. We're not looking at the actual changes of the state point, and we'll dive into that a little bit later. So some fun facts, right? It's got to make light of it all. I'm a believer of looking at where do words come from, like the etymology, the origins of words. So I've got a prize for the first one that can tell me, online or in person. We've got psychros, meaning cold, and metron, meaning measure. So cold measurement, right? Anybody have any idea of the origin of psychros, metron? Okay, no awards for anybody, but it's Greek, right? Greek, Latin is another fount for a lot of words, but Greek, a little etymology there. But then here's a fun fact for you guys: the CIA was actually using the LSD back in the 60s. They were trying to find a truth serum. They wanted to, when they interrogated people, they wanted to be able to get the truth out of them. They actually used a number of different declassified drugs, but they started hosting parties in the San Francisco Bay Area where they would open up a house and they would invite people in. And they would use an aerosol spray that basically dosed the party. And they would sit behind the closed doors or two-way mirrors, whatever it is, and they would monitor all this. They would see what happened. Well, unfortunately, that backfired on the CIA because people started to think for themselves. But after so many doses, after being dosed so many times, they started to realize that what they were doing, and so the CIA found that it was not useful anymore because they weren't going to get the truth out of them because, like I said, it backfired on them. So a little fun tidbit, well documented out there, but yeah, thanks to Mr. Uncle Albert, right? Uncle Albert contributed to that in some way, shape, or form. So
it's a fancy little effect there, Jason.
I'm doing what I can.
It's not lost on me. Those transitions in PowerPoint, they're powerful.
So we've got the holy grail of air properties, right? I think there's a lot to be said. You can look at the image, right? All these eyes looking back, all looking on you, and at any rate, there's going to be a lot we get out of this. This is be good. So when we look at psychometrics, there's a lot of things on that psychometric chart. There's just a lot, right? So we've got dry bulb temperature, we've got wet bulb temperature, we've got dew point, we've got a humidity ratio, we've got enthalpy, we got vapor pressure, something called the sensible heat ratio. I'm stoked that this chart's in front of you because it aligns with the chart that I'm using, so it'll mesh well. We're getting the relative humidity and specific volume, which we'll use relatively frequently to account for the varying conditions of the air that we look at today. So this is the chart that I use periodically quite a bit. Sorry everybody, I hit the microphone there online, that was loud. But I use this train chart. It's very handy. This you'll see aligns very well with what Tom has in front of us. Sometimes up here in the corner, you'll see a little protractor for the sensible heat ratio. I don't like that one. It's hard to transpose that line, which we'll talk about later, then onto this chart when you try to take it from the protractor up here. But this one will work out what you have will work out fantastic with what I've got here. So, but everybody makes a psych chart. What do you got? Temp Master here. You know, I mean, every manufacturer in this industry is almost making a psychometric chart. There's a little bit different spin on it, but it's all the same information. So I'm glad things line up for us today. This will work out quite well. So dry bulb temperature. We can measure that with a thermometer. That's easy enough, right? We can come in and measure it. There's absolutely no moisture on that surface that we measure it. So it's just what we feel. That's that dry bulb, that temperature that we try to control in buildings. So what is the dry bulb temperature on here? This will be a straight vertical line, and that dry bulb is measured right across the bottom of our chart. There are some charts that will go down into like -10, maybe 0. This one that I typically use goes down to 30. What do you guys got here? You guys go down to -10. Look at that, fantastic. Because we do in our area, we do deal with temperatures down to that degree, right? So very handy. Next, we've got the wet bulb. We're going to measure that with a psychrometer. Basically, the wet bulb is the temperature at which we're going to get evaporation of water vapor at a constant rate in any particular mass flow rate of air. And so that is going to be found then running from this curved line all the way over to this, it's running in this direction, and these green numbers here, that's our wet bulb temperature. And that is these green lines as we run across. So that's our wet bulb temperature. We look at humidity ratio. That's going to be, in my chart, what I'm using is grains per pound. You guys are also grains a pound, so that's fantastic. So that's the amount of moisture that we can hold in any temperature, any state point of air. That's what we can hold for moisture. And so as you can see that ratio is the ratio of moist air, that weight of moist air versus the difference of the dry air and the moist air. So sometimes they're going to call this like the absolute humidity, which we can get this pounds of moist air per pounds of dry air by converting our grains of moisture that we get off our chart and dividing that by 7,000. That'll convert that into a very small number. Because right now we're dealing with whole numbers there from 0 to 200. When you factor in 7,000 to convert this into the absolute humidity, it's a very small number. And then we've got the dew point. Dew point is the point at which condensation is going to occur. If I had a cold beer in here right now, I might have condensation. If it's warm enough, I might have condensation on my glass. You know, at that point, you've reached the dew point. So where are these guys on our psychometric chart? Humidity ratio is running horizontal, straight across. And actually, that humidity ratio here, like I was saying, that's our values from 0 to 200. And then when we get to the dew point, dew point itself is also right here, just to the right of it. Same as for what you guys have in front of you. So like I said, dew point is the temperature we're going to condense moisture out of the air. Relative humidity. People like to deal with relative humidity, but that's the amount of water that can be held in air at any given point, any dry bulb temperature. So the warmer that air is, you can just, again, looking at a chart, it's worth 1,000 words, right? The warmer our air is, the more moisture we can hold. Colder that it is, the less that we're going to be able to hold. So we've got this curve. These curved lines is our relative humidity. And that goes from 10 all the way to 90, and then when we hit 100% relative humidity, this is what we call the saturation curve at 100%. That's this far line. It's completely saturated. We've got 100% water in that water vapor in that air at that point at that temperature. enthalpy, energy. Right? We're dealing with energy every day, every single day, whether we fully recognize it or not, but we deal with it, and that's the amount of energy that's in the air. That's total energy when we look at the enthalpy. So we can take, so sensible energy is related to the temperature. The total energy is related to the latent energy and the sensible energy that's in the air that we're dealing with, right? So we've got total energy, sensible plus latent. So when we look at where our enthalpy is here, it's not quite parallel to our wet bulb temperature. And the charts not every line of enthalpy is parallel to itself. It does change a little bit as you work your way down through the psychometric chart. But they are not, enthalpy is not parallel to the wet bulb temperature at all. So that's why they give you this, that's why I like these charts. They give you the enthalpy over here and they give you the enthalpy here so that you can draw a line between both points so that you ensure that you've got the line that you need, that it's not off kilter. Works out pretty handy. In all honesty, I didn't realize until I was putting this together that line of enthalpy does actually change because this line here, if I brought it down to here, it wouldn't line up with 30 to 30 here. So I'm learning things as I go through presenting this, or putting this presentation for you guys.
I've got a question.
Yeah.
So everything is based on temperature and how much water is in it, right?
Yeah.
Why do we have so many terms?
What's that?
Why are there so many terms?
Why are there so many terms?
They're all.
There's for different reasons, right? Let me just go back for a second here. Pardon me for doing so. But when we look at, let's say, dew point, you have an OR space, and you've got people gowned up, and my hospital wants me to have the OR being 68 degrees and 35% RH. Okay, 68 degrees, 35% RH. Let's say 40 will be an easy number. I got to follow this over. It's going to give me a dew point temperature according to that temperature that they want me to maintain. Well, in an OR, people are gowned up, right? They're in a suit. They're protecting the patient from themselves. Well, if I don't want them to sweat inside those garments, I need to make sure that the air that I deliver is at or below the dew point. If it's above, I'm never going to be able to keep them happy. And they're going to come back to me and ask me, why are we sweating in here? Right? My point is, my design has to be according to keep the dew point, in this case, where it would be 68, 40, is right here, roughly 46 degree dew point, 47 degree dew point. Well, that air I got off my cooling coil needs to be at a dew point below that temperature. The ambient temperature can be above there, but at that dew point, I need to be able to control that dew point. So there's, it's not just the relative humidity that we look at, a lot of like standard conditions for our typical office building, 75 Fahrenheit dry bulb, 50% RH. Well, that's 75 at 50 is somewhere right in here. That's a dew point of 50, 55. 55. Well, it's a typical design of coils. Give me 55 degrees off my coil. Right? That's going to be back over here saturated. Well, that is allowing me to maintain that dew point. So we have to make sure then, in my case, I just said an OR, that we've got a dew point temperature low enough for the users of the space, which means that I've got a low temperature coming off my coil, maybe at 45 degrees or 48 degrees, whatever that dew point is. But then I can heat it back up. I can heat that back up, but I'm still going to be at the same dew point. It's constant, even though I added sensible heat to it. So I can still maintain the space at 68, even though I'm delivering 48 degree air at a 48 degree dew point.
Hey, Jason, Chris Stipe put in the Q&A that he can't see the pointer, so you may want to.
Yeah. Is this the one? Okay. Perfect.
This is just a problem in general, so.
Sorry, Chris. Sorry about that. When next time I start pointing, I will.
Chris, you should have just showed up live. There's one seat left.
Okay. Tom, thank you for the question there. I appreciate that.
Sure.
Everything is useful. As you will find out, everything on this chart is useful. It's all matter of perspective and how we look at things. I guess that kind of ties into the theme, how we look at things. We leave off on enthalpy, specific volume. So it's the inverse of the density of air at any temperature, degree of moisture, is what that is. Bless you. So specific volume, good thing I animated this, right? So specific volume is coming down on the green lines. Can't quite, they're kind of faint here, but they come down and forth, back and forth like this. On this, I will say, I think it starts on mine at 13 or 12.4 on the far left, and it goes up to 15.8. What do you guys got? Since you guys go down to minus 10.
12 to 15.
12 to 15? Okay. So density of air is important. That's going to be how we correct things when we look at our mass flows later on. Vapor pressure, that's a biggie in buildings, right? If anybody ever notice on brick facades, any white powder that's on either the inside or the outside of buildings, it's called efflorescence. That's due to the difference in vapor pressure from the outside to the inside. So that vapor pressure is going to go from high to low, right? So, and it's got a number of components to it, as I'm showing here. And they're all related, all those components, each have a partial pressure, they make up the total pressure. And this is dirty, right? So this has got contaminants in the air, and that's what that, the white powder, that's basically minerals, right, from the air. As it condenses out, it leaves that, as the vapor, it works from high to low across that building envelope, it's gonna leave a residual or that dust. You know you have a problem at that point. So that's why we put in a vapor barrier on our building perimeters, on the exterior, whether it's outside the insulation or inside the insulation. Is a whole other science to that, but so I use vapor barriers in our buildings. And that ratio is directly impacted by that vapor pressure itself. Lastly is the sensible heat ratio. Like I said, this is a great chart that you guys have because this will work well for us, but that's just the ratio of the sensible heat to the total of our system. So vapor pressure is our first one. Again, that's riding that same line of the humidity ratio and dew point, and that's coming over on the far right-hand side here, up and down. That's our vapor pressure of the that state point of air. And then sensible heat ratio. So you'll notice a little dot on your psychometric chart right in the middle. That dot at 75. That's go figure, 7550. That dot is what you're going to end up using to draw your sensible heat ratio line later on. So you go from that point to whatever the percentage is. So the sensible heat ratio percentage on my chart here is this green inside of marks, ticks of the outside border, while the vapor pressure was on the out. Sensible heat ratio is on the inside of that same area. So we'll go back once we know if you know your sensible heat ratio, your sensible to total heat, you can draw that line from the middle over to that percentage, 70%, 50%, whatever it is. And, I'll sort of show you how we use that later on. Am I going too fast for anybody? No. Okay. Let's look at a state point. So why don't you guys plot 72 at 40% relative humidity, and we can find these five other points. I shouldn't say points.
Quick question for you. Yeah.
Yes.
Out of curiosity, what is that point at 78 degrees and 50%? 78 degrees Fahrenheit and 50% RH. What did I miss? That?
Oh, so that the point on the site chart, if they're using a similar site chart that we have here, what I have on the screen, that point in the middle there, that dot that you see, for my chart here, it's at 78 and 50, but now your chart is different, 75 at 50, right? So that point has been set by this manufacturer to give you then the correct corresponding sensible heat ratio on the far right-hand side. So we've got two site charts in front of us. Each one has again, a little bit different, but they ought to give you the exact same percentage when you look at that sensitivity ratio. I hope I answered your question. What everybody did for a wet bulb? Anybody find a wet bulb? Here's a point. Any takers?
57.
What's that?
Up 57.
57? Oh, there's our line for our wet bulb, right? 57.3 to be close to exact. So, Mr. Katzen, you get your first prize of the day, some gummies.
Are these special dummies?
Those are not double gummies.
Okay.
You'll have to live in Illinois or Michigan, Minnesota, anywhere around us.
No commentary.
So what was our next one? We wanted to look at, this is probably humidity ratio and dew point. Looks like, anybody come up with anything? First time I went to college, I didn't answer questions either. No offense, I take no offense.
46 grains per pound.
36 grains per pound with a corresponding dew point of
47.
46, right?
Okay, so that's what we got. We got a dew point of 46.5, nice. And then we've got a humidity ratio of 47 grains. You hit that one on the head, bud. There you go, sir.
So Jason, that means that if the surface of your cold beer can is at 46.5 or less, moisture will start to condense.
Correct. Once you hit that, you're gonna start to get condensation on your glass. I don't have a glass of beer to show us right now, but we could have that conversation later if we want. May I ask you anything else? So this was the specific volume, it looks like, that we're looking at for that 72-40% RH. So with that, 13.55. So just so you know, there are online tools, calculators, that you could input this point, the 72 at 40% RH, and it'll give you all of these points, right? But if you just did that and didn't quite understand all of this, it might not make all the sense. So like I said, I'm not an expert. I'm sharing what I've learned in my life experiences in these topics. And so that's the fundamental background of it all will serve you well as you go forward. Even a refresher, right? Like I said, I discovered that the lines of enthalpy aren't parallel to themselves as you work your way across the site chart. So now that could be this. It might be different on this one from TechMaster. I don't know. But from what I'm using the train one, I was enlightened by the train company themselves. So then when the last one's enthalpy, right? You can see they don't quite ride parallel. Right? We're up a little higher on the bottom right and down a little lower on the upper left. So that wet bulb and enthalpy they don't ride the same. They don't ride the same line. And I had 24.6 BTUs per pound mass for the enthalpy. So obviously there's a lot of information built into this chart, and where do we get to go? What are the things that we can do with this, right? With this tool, because it is a tool. But if you don't know how to use the tool, then you can't solve problems. But if you understand what tools that you have at your disposal, I think we're extremely dangerous to solve problems for our owners, our clients, whatever that may be, right? The more we know, the better off we are. We don't necessarily know what we don't know until we find out that we know it. I said that correct. Because that's happened to me in life, for sure, and in work. So the first thing, we're going to look at heating and humidification. When we go from that center point off to the up and to the right, we have added heat and we've added moisture, right? We've increased the dry bulb temperature and we've added moisture by the grains per pound. So an example of that, little air handler here, we bring in outdoor air, we preheat it to some temperature, and then we add moisture to it to maintain the space at whatever condition our clients, our owners need it to be. We got sensible heating only, and that's that's a coil, like a reheat coil on a VAV box. You basically take air from 55 and you heated it up to 70 degrees. You've done nothing but add sensible heat. And that, again, that's horizontal across the bottom of the chart. Strictly added heat. Chemical dehumidification, we're, as you can see, we're adding heat by going down and to the right, and we're removing moisture. So when we look at that, would be a desiccant wheel, silica, gel. What we're doing is we've got two streams of air. We've got our process side that we want to strip moisture out of. Well, that's interacting with a wheel that's very hot because you've got activation or reactivation there, excuse me, that sometimes we use steam, a steam coil or gas fired, or I suppose you could even do electric, but you add a bunch of heat to that wheel to dry it back out as it rotates. Slowly rotates, I take moisture out on the bottom, and then on top, I'm stripping it of moisture, and then I dry that back out so I can just keep that process going. Continuously goes through. I think this was from Munters. In my day-to-day, I've got a lot of Munters cargo carrier units that were humidifying air to dry it out to serve various processes. But I've added heat to it, so you have to take that into account. Now I got a post-cooling coil downstream of all of these so that I can cool that air back down after I've heated the snot out of it, because sometimes I could be 100 degrees, but I'm extremely low on my grains of moisture. I could be at 8 grains of moisture. You could, static, you sort of have issues with static at that point, I suppose, but I wring out all the moisture, but I've added heat, and I've got to strip that heat back out. Dehumidification, that's strictly, all you've done is you've taken moisture out. You're staying, if you're at 75 degrees and you want to strip that moisture out, you're going to be at 75 degrees Fahrenheit, dry bulb, but you've removed the moisture. So an example of that is, well, like I said, Minnesota, Michigan, Illinois, they've all got these shops, these plants need to have a well-maintained space. So they need to strip out all that excess moisture, right? So this is strictly a liquid desiccant would be an example that there's just stripping out the moisture. That's all they're doing without changing the temperature of that space. Cooling and dehumidification, we're gonna cool down that air. We're gonna dehumidify, strip out some moisture. Again, we got an outdoor air damper. We're bringing in that outdoor air, go across our cooling coil, and then in the process, we are dropping it down in temperature, which then also lowers the moisture level. On the flip side, you could do sensible cooling only, which you're not going to take any moisture out. You've designed that coil explicitly to take heat out and not remove moisture.
Chill beam.
There you go. Evaporative cooling. Now that, I'm going to say for evaporative cooling, we're going up and to the left, so we're cooling and adding moisture to it. Basically, we bring in hot ambient air, we cool it down, but there's going to be more moisture in it than it was when we first got it. And that you can simply a wetted surface that you're just pulling that air across. I will say for the evaporative cooling and the chemical dehumidification, you stay constant enthalpy. You're not changing the enthalpy of that air as it goes through those devices. And the flip side, when we talk about humidification only, which we are all familiar with, we could use steam. This is injecting it into the air. You could have it in a duct system as it leaves the air handler. You've added moisture, you've not changed the temperature. So dehumidification and humidification, you have that, you're constant on your temperature, on your dry bulb temperature. You have not altered your overall temperature of the air. Any questions on what we get to do with the psychometrics chart? What we can do?
That's good.
Some fun facts. Yeah, these are good. So back in my early days, I used to live with some of this artwork. One of them was Adam and Eve, and this is a depiction of, we'll say they both ate the apple at the same time once the serpent told them to eat it. I'm not going to blame one or the other. They both ate the damn apple, and here we are, not to get but, so you got the serpents, you got 7 heads on that serpent, and poor Adam and Eve, they ate the apple. We got the Firewalker. This was a 7-foot tall painting, about 3.5, 4 feet wide. It was in our living room. It was massive, and it was it depicts somebody walking coals, right? You hear some of these ancient cultures that would walk coals to purify themselves. I'm not sure I would do it, but it had to be hot. But this was in my living room. It's in a museum somewhere in the continental United States at this point in time. And then the promises. This one's probably a little bit more deeper. If you look at the photo, there's a lot going on within it. You've got a man and a woman, you've got their child, you've got a baby within the womb. You have a spirit that's combining, that's really connecting the two of them. The two of them, it could be however you want to look at the universe, binding the two together. But then you have the silhouettes on the far left and the right of the man and the woman. The man is holding his sword as a warrior, and the woman is next to the tree of life, Mother Earth, I guess, as you could look at it. A lot of stuff you might not be able to necessarily see. There's some things inside here, but these are all 3 very colorful pieces of art that I used to live with in my young 20s. I'll be 50 in July. Looking forward to it. Celebrate life. Celebrate. How are we doing on time?
Are you going, is your pace too fast?
I don't know.
Yeah, no, we're gonna take a break in
Perfect.
whenever,
Okay.
15 minutes.
So what are some processes that we can do with the psychometric chart? We went through all the things that you can do. We're going to dive into a little bit of each one of those as we roll through here. So let's look at combining air streams. We do it every single day, right? We do it every single day. Outdoor air, return air. So we'll do this again as an example. I think I've set this up to where you guys can participate. We've got an air handler with an outdoor air load of 30%. Total supply airflow rate of 10,000 CFM. Ambient summer design conditions are 95 dry bulb and 75 wet bulb. And return air from the system on a design day is 76 degrees Fahrenheit at 55% RH. I want you guys and gals to tell me what those mixed air conditions are after we've mixed them. If you don't know, I can walk us through it by all means, but if you do, take a stab at it. Take a stab at it. I'm going to show you where we're at. This is my crude schematic of what we're looking at. Right, we've got volume of air, which 30%. So we got 3,000 CFM, 7,000 CFM at varying states. They're merging together in this air handler. So here's our state points, point 1, point 2.
Okay, so what was the indoor condition?
76 at 50. No, it's 55, sorry. 76 at 55. So we've got our 2 points. So we know a lot of information with that already, right? So first, if we look at the total, let's find that total weight, right, of each airstream. And that weight, what I mean by that is the mass flow rate. That's going to be our pounds per minute. So we take our 7,000 CFM, and based on that indoor condition of 76 at 55, our specific volume is 13.73 cubic feet per pound mass, which gives us just under 510 pound mass per minute. That's our mass flow rate of indoor air, or return air. The outdoor air, similarly, but that has a different volume, specific volume, right? We're at 14.28. So that gives us 210 pound mass per minute. So we combine those two for a total weight of 720 pound mass per minute. So that's our total weight of our air. Now, we want to know what temperatures, right? We're gonna figure out what the temperatures of those, the total at the end. So we take our ratio of 509.8 over the total. So that's the indoor air over the total weight times the temperature of that return air of 75. Oh, I got a typo. I have 75. Pardon me, I said 76. See, I made a mistake. We're gonna keep using 75. So, like I said, we'll roll with it. At 75 degrees, it correlates to 53.1 degrees. We look at the outdoor air times 95 degrees Fahrenheit. We end up with 27.7. You combine those two, we're at 80.8 degrees. So with that 80.8, we can find ourselves right here. We just go from our dry bulb temperature up to that line, right? We said this was our line, we connected those 2 points. So we ride that line and we're at 80.8. Now based on that, we know everything about that mixed air condition. We know the enthalpy, we know the wet bulb, we know the specific volume, we know everything about that point. So with that, we also know our additional properties of wet bulb is 67.6, our dew point is 61 degrees, total enthalpy, or the enthalpy of that state is 32 BTUs per pound mass.
Jason, if I had just drawn a straight line between the two of them and went 70% of the way, is that the same thing?
It is not, because you can get close, but you won't. What you're not doing with that when you're using just the temperature is you're not taking into account the difference in the volume of the air. Right, so there's, later on I use long road and we take the short road. So the short road does that, takes our common formulas, like our simplified HVAC formulas. That's based again on that 70 degrees, that standard condition of air that we standardized way back at the beginning. When we use the psych chart in this manner, this is taking the specific properties, not an assumed value that you're going to be plus or minus at that point. So this will be exact. I shouldn't say that. It's exact, more so exact than the general formulas. But there's also, you're subject to the interpretation of how you plot this out on the chart, right? So again, like if you find a tool online, you put in your 76 or these points, it's going to give you the explicit values. I had a professor at MSOE that was, I don't know how the hell he was doing it, pardon my French, but I think he was using a computer to get the exact, and he would knock us points for being 2/10 off or some, just, most people didn't like it. I like all you guys, gals, so, but this would be a more precise way than using a generalized formulas now. There's a time and place. Heating only. So here's another one that we'll look at. So this was we're just adding sensible heat, right? We're moving straight across to the right on our chart. We're not doing anything else other than moving to the right. So we take room air, we got 1200 CFM being recirculated via a fan powered VAV terminal with a hot water reheat coil to wash the building glass facade. Probably a lot of us will do that, right? We got all these architects, if there's any in the room, forgive me, but they like a lot of glass. And we have to keep the perimeter of the building conditioned. We don't want condensation on the glass. That's their fault because they didn't specify the glass properly, but it's our job to protect them and the building owner, so we're gonna wash it with hot air. While the inlet air conditions are 68 Fahrenheit, 35% RH, I need a discharge air temperature of 95 degrees to handle that load. So what is our hot water reheat load? And we're gonna take, like I said, there's 2 roads that we're gonna look at here. So let's dive right into that. So sensible heating only, here's our little crude schematic, and we got a coil, we're gonna add heat to it. So the point 1 gets heated. We got our points right here, moving from 1 to 2. Again, those 2 points tell us a lot of information. So our overall energy balance of that system, we've got that mass flow rate of 0.1, and it's got an enthalpy associated to it. Now we're gonna add heat, which is gonna make us that mass flow rate of 0.2 and its enthalpy, right? It's gonna change that. So we're gonna move some things around, simplify that equation, to find out what that sensible heat that we're adding. We need to find the overall mass flow rate. We've got a CFM I gave you, right? So we're gonna move into that first. So the long road, we've got find our mass flow rate, take our 1200 CFM per minute. We're gonna divide that by that specific volume. That's the inlet condition, right, 0.1. So then multiply that by 60 to get us 5,821 pound mass per hour. That's our mass flow rate going across that coil. Now, we're not adding or taking any air out of that, so the mass flow rate of 1 is gonna be equal to 2, right? So now when we look at this, we're able to simplify that equation up here because the flow rates are the same. So we're gonna take that 5,821 pound mass per hour, and we're gonna multiply that by the difference in enthalpies of 0.2 and 0.1. With that, we get 38,420 BTUs an hour is our reheat load. That's our reheat load that box will see. Tom, to your point, the short road, we're gonna take a look at just the delta T. We're not taking into account anything in terms of the actual condition of the air. So that 1.085, that's a factor that's comprised of the specific heat, the 60 minutes per hour. So we've got 1.085 times the CFM times the delta T. We get 35,154 BTUs. So what is that, 10%? Is that 10%? 3,000?
The constants that you've got, the 13.4.
That is,
1.085.
that's this guy right here, right? We're taking this, that's our specific volume. Then we've got the specific, that's what gets heated. So that's the 13.4. There's a little bit of change as I had it on there. So we use that to define our overall mass flow rate, because I gave you the CFM. So I need to convert that into pound mass per hour. That makes sense?
Not for me.
Anybody else lost on that?
Raise your hand if you totally got this.
2 people
I
got it.
took the short road.
Let's go through it again slower.
Yeah, no, not a problem. So let's go back. So we've got 0.1, right? We've plotted that.
A
Now,
lot of that.
yep,
Oh, and then you're going.
we
this
take the
upper-
specific volume, which
almost
is,
straight up and down line is your what?
that's our specific volume. That's the specific volume of that air at that 70, what did I say it was?
It's not super clear on this chart. Oh, I see it. It's this, there's this
Yeah, there-
13.0 volume.
Yeah.
Volume,
Yep.
cubic feet per pound.
Yep.
Right, so we're sort of picking a spot in the middle of that.
Right, so if you use a tool, an online tool, it's gonna give you the explicit value at that. So this is the subjectivity of using psychometric charts.
Yep.
Just saying.
What did you use? Just a little bit more than.
I use the psychometric chart.
Okay, so all your values are your
Yeah,
interpretation.
There's more, yes, there's more lines here than there are on yours, so in terms of, if I take 13.2 and 13.4, look at where the middle of that is 13.3. Now, where am I at between 13.3 and 13.4? 70% towards, it's trying to be as, without using explicit values, this was the best way that I could share the subjectivity.
So if you're here, there's this 13% or 13, whatever that ratio was, cubic feet per pound dry air, and then
Yep.
over here is the 14.
Yep,
You kind of draw your point
correct.
almost straight up, but a little.
So straight edge.
And that's where that number came from.
Correct. Straight edge comes in handy, obviously. So that's where I got the 13.4. I don't have, Green X got an app, I'm sorry, Cook's probably got an app out there.
Sure.
Good save.
Sorry, I didn't, that was.
Kill me, swallow.
So we convert our CFM into a mass flow rate, which gives us that 5821. We utilize that mass flow rate, we multiply it by the change in enthalpy from 0.2 to 0.1, which gives us the total reheat load on that VAV box coil. Now, like I said, you can take the short road, and that short road might not always be the best road, but you can simplify that by just looking at the change in the dry bulb temperature, multiplying by the CFM and our factor of 1.085 to get us 35,154 BTUs an hour. So there is about a 10% difference there.
So I'm looking for this 28.4 and 21.
So that's enthalpy. Let's go back.
This one.
Yeah.
This chart.
So I got I1 and I2 is what I plotted right here. So I1, I2, all corresponding. So you got to look at the other lines now that are at a little bit more, a little less of an angle, right?
Oh, so this is the one that's wrapping around.
Yeah, yep. So for yours, let me walk over. Yep.
You should use a string, you can make this.
Yeah.
So this is your enthalpy here. And then your other enthalpy is this one here. Correct?
Oh,
So you
they're the
can,
same.
correct.
All right.
Draw them, you connect both sides, and that'll be your straight line to define your point.
They're not parallel, right? These ones.
Everybody follow? Everybody online good? Sure.
So you said 21 and 28, all right, I see that.
Yeah. So I had, 28.4 and 21.8. Now the enthalpies broke down into further degrees, or I shouldn't say degrees, but points. There's more points on that, on the side of the enthalpy. Where the specific volume, you could have a gap. Like, what do we got here? We're going from 15, what's the next one? 14, there's a intermediate one, which must be 14.5, right? So there's less lines on what's here, versus what I've got on what Train has, I should say. There's more lines to correlate to. But I just want to show that the short road of not taking into account the specific volume of the air.
So you're up by 10%.
Correct. Yep. We'll look at another one of just cooling. So just cooling, only sensible cooling. Preconditioned supply air of 575 CFM delivered to a post-cooling coil to serve an internal process room. Inlet air conditions are 70 degrees Fahrenheit at 30% RH. Discharge air needs to be 60 degrees Fahrenheit. So what is our post-cooling sensible load? And again, we'll look at both the long road and the short road. So when you plot your points of our generic little schematic here, we're using chilled water. We're pulling energy out. We've got our points plotted here, and so with that, we know our specific volume. We know our enthalpies of our conditions. Give me a sec to do that. And our energy balance, is a little bit different than the heating, right? Because instead of adding heat, now we're pulling heat out. So we've got that first mass flow rate is going to be equal to the sensible heat that is in the air combined with the energy of 0.2, right? So we get the sensible, what are we taking out? We're going to take that mass flow rate that we find here and multiply by the change in enthalpy of those two state points. So again, we go ahead and use the specific volume of 0.1. And we're going to convert that 575 CFM. I had 13.2. Anybody else, anybody get different or drastically different than 13.2?
I need your original numbers again.
Original numbers, sir. Go back. I've got 70 degrees Fahrenheit at 30%. My second condition needs to be at 60 degrees Fahrenheit. Again, we're just moving straight over. Right? That's all we're trying to do. We're going to move straight to the left. So at 0.1, should I 13.4 and change is what I had. Oh, wait a second, 13.2. I used the wrong state point. My apologies. I used 2 instead of 1. Okay, that's okay. We can adapt. Life is adaptable. So instead of the 13.2, it looks like we're closer to the original point of that specific volume was at like
13.4.
13.4. Okay, that's my fault. So we're gonna be at something a little bit different than the 2614 pound mass per hour. But we're gonna utilize that mass flow rate then when we look at the change in enthalpy of state 1 to state 2. There's not much of a change there, but our coil needs to remove almost 6,000 BTUs an hour for that post-cooling coil. And again, I see this a lot in my pharma applications. We've got a lot of post-cooling coils downstream of VAV boxes or airflow station of the control damper in a coil instead of a reed coil, so that we can maintain cooler temperatures within our process room. So if we then look at the short road, again, we're just going to use the change in temperatures. We're going to take our CFM times that 1.085 factor and multiply that by the change in dry bulb temperature, which is just a delta T of 10. So we come up with roughly 6,239 BTUs a pound per hour, excuse me. Again, there's a difference. The difference will be greater, obviously, because I made a mistake in my the point that I used, so my apologies. Again, just want to be able to show the differences in how we calculate things. Short road close enough for horseshoes and hand grenades? Sure. Do you need something explicit, nailed down to the bottom dollar? Take the long road and use an explicit tool online to get you the exact values, so you're not subject to the interpretation of using the chart. But again, when you add the heat, right, so that's gonna, after you've cooled it down, you're gonna slide horizontal, yep.
And it depends on the temperature.
Correct, so you're just gonna slide to the right, on your temperature, on your dry bulb.
Yes, sensible.
Yep, yep, you're not doing anything else, it's just sensible heat that you add to it, yep. In that sense, you're not bringing out moisture at that point, but you're changing the relative humidity of it, right? As you slide across there. And that's where sometimes people get into trouble, is you just, I lowered the humidity, but you didn't take any moisture out of the air. You know, there's still too much moisture that is impacting the building occupants.
So basically, you just burn all the water.
Yep, yes, correct.
All right, it's 11:07, let's go.
All right. So we're looking at a constant volume air handler delivering 12,000 CFM, cooling and dehumidifying. We do this every single day. 12,000 CFM of supply air delivered to multiple office spaces. Mixed air temperature is 78 dry bulb and 65 wet bulb. Requires a supply air temperature of 55 that it's nearly saturated. So we're gonna look at the total heat transfer across that coil, and we'll look at the long road and the short road. Here's our coil. Got chilled water. Now, instead of what we had before, was just sensible cooling, we are also taking out moisture. Right? We're dehumidifying, so we're pulling moisture out of the air. We've got our 2 points upstream and downstream of our coil. So here is our site chart when we look at both of them. So how do you get to 0.2, right? So on my chart, I have these, not everybody has it, but you see these cooling coil lines. These lines here that kind of dip down, very faint. So I'm following what I did. I take our state point 1, and I'm going near towards that line of saturation, and I'm curving down. And I'm not going to that line of saturation, but I'm going close to it. Typically, if you look at a air handler or coil selection, it's going to be 55 at 54, right? It's never going to be 55 at 55. So that's the principle that I use here. Is I've gone down to 54 degrees. I've taken it to the 54, not to the line of saturation. So that allows me then to get a difference in enthalpy, and we're going to look at the change in the moisture that's in the air, because we're bringing it out, right? We're taking moisture out. with that, so now it's at 0.2, you know what your, the amount of moisture that's in the air, you got your dew point and everything, and, your enthalpy and such. So when we look at this, and we've got our energy balance is a little bit different. We've got still that same, the energy that's in the initial state of air, but that's equivalent to the amount of heat that we're gonna pull out, the energy that's in the discharge side of that coil, and then there's also energy in the moisture that we wring out. So everything on the right is what that coil is doing and what we need the coil ultimately to do. So we're gonna isolate that mass flow of the water through some tricks of math. No tricks, I guess, it's actually just the way it all works out, kind of fun, call me a nerd, but we get the mass flow rate as constant for all of those, right? Because we're not adding any air, we're not taking any air out. So the overall mass flow rate times the change in the humidity ratio, so that W is. When we get that flow, we've got 12,000 CFM, gonna convert that to CFM per hour. And then we're gonna take our specific volume, which I found to be 13.7. Is that, everybody else get 13.7, or did I make another error?
Yeah.
Close enough for horseshoes and hand grenades? So I get 52,550 pound mass per hour. That's our mass flow rate of the air going across that coil. So when we simplify that mass balance, again, we solve for Q dot, which is the amount of energy that we need to take out of it, out of that airstream. We're gonna take the energy related to the enthalpy of the air, and then we're gonna add that to the energy of the water that we're wringing out, the moisture that we're wringing out of that airstream. So with that, we've got our 52,550 pound mass per hour. We know our enthalpy of that between state 1 and state 2. So take that difference. Then what we're gonna do is we're gonna add to it the change in the humidity ratio of both of those points. And I came up with 72 and 62.2 for when I came up with the psych chart. Let me just go back and make sure we're good. Bear with me. So if I look at state 1 up here, 70, just under 72, and I come back here straight across and I'm just above 60, so that should make rhyme and reason here, 72 and 62.2. So we're gonna add those two together, which I've got, but I need to convert that with that 7,000 factor again that we talked about at the beginning of the presentation, and that's in pound mass per grains. Okay, so we convert that our grains per pound, and then what we end up getting after we multiply that by the enthalpy of the water, which was 22.8 in mine. How did I get that? Let me just go back one more time. So what I did to get this point here is once we establish this condition coming off the coil and we have our horizontal line across the chart, I came down from point 1 and I needed to know the enthalpy, so I had to find a parallel line of enthalpy to get over here from, that's related to the moisture in the air that I just pulled out of that, what we're pulling out with that coil. So you've basically we created a triangle, and so that allows us then to determine what we are pulling out energy related to the water, the vapor that we pulled out across the air. So when we look at this then, what you're gonna see is that value of what I have in yellow here, this energy is related to the moisture, that water that we wring out of the airstream. You can see that's very, very small, right? Like I said before, you take the difference of 72 and 62.2, you're 9.8. When you divide that by 7,000, you've got a very, very small number. So when you multiply a very small number, or a number by a very small number, you get another very small number. Not as small, but a lot of people neglect this. But I wanted to show you that there is energy there. There's a certain BTU per pound mass, but it's it's very small.
This is energy that's in.
So yes, correct, that's the water that we've run
Water
out,
that's getting wrung out
Yep.
has energy in it, you're
correct.
attributing.
And that, we were able to find that by making that triangle and taking it back to the, point of enthalpy.
Could we say that the first term is sensible load and the second term is latent load?
No, the first term, this term right here, this term is total. Because we're looking at the difference in enthalpy. Enthalpy, change in enthalpy is total energy.
No, I mean from the energy equation, from the first line.
Oh, you're up here?
No, on the simplification.
That's okay. So this is total, we're looking at, that's the enthalpy, change in enthalpy. That's gonna be total energy that we're looking at. And then this is the condensate that we rang out. Right, that's because that coil is doing two things. It's cooling and it's dehumidifying, so there's two aspects to it. Let me see, did I say that wrong? We rang moisture out, right, there's a change in moisture, but we've also cooled and dehumidified that air.
This would be a very high S to T ratio coil.
High S to T in terms of sensible to total.
It's almost all sensible, right?
This would be almost all, I mean, this is nearly all sensible, correct? So I guess I stand corrected. I would say that would then be, it's more sensible than latent by the amount of moisture that we took out of that. Well, when we take the short road, so here's another equation, 4.5 times the CFM times your change in enthalpy. This is total energy, but that factor that's BTU per hour over CFM times BTU per pound mass. Okay, this is a common formula that 4.5 times the CFM times the change in enthalpy is, you see that on your chart. They've given you a couple other equations on there as well. So when we look at that, just looking at the delta, because we haven't corrected the airflow yet for our initial condition. We've assumed that it's at standard pressure, temperature and pressure, right? Which is not 100% correct. We've got 345,600 BTUs. We have that here, 337,998. So there's a difference. There's a difference in that, but a much simpler approach than using the mass flow rates. So we want to find the moisture that we wrung out. How much moisture did we pull out? Well, that same 4.5 times the CFM, but now we're going to look at the actual difference in the humidity ratio. That's where we were able, we found that humidity ratio by drawing a straight vertical line from our 0.1 down to the horizontal line of 0.2 and transposing that back to the enthalpy. So that gave us that 23.5 grains. 23 is the 0.2. So when we look at that, we pulled out 142 pound mass per hour of moisture. That was the amount of water that we removed from that. This is another one. I mean, I suppose if you're looking at condensate pumps, right? If you needed to pump your condensate from your coil, if it wasn't going to a sanitary drain, it needed to be collected. You could utilize this then and say, how much condensate am I going to get on a design day? And I've got to be able to move this much condensate.
You just take your pounds divided by 8 to get your GPM.
Yeah, you can convert this over to 8.33, right? Yep, you can convert that to GPM, exactly. Yep. So going back to your question, right? You asked if it's just sensible only at that point if we neglect it. When we look at this, then we can use the sensible heat ratio now to find out how much of that is latent and how much of it is sensible of that total load. So taking 1.085 times our change in temperature, divide that by the 4.5 times the overall enthalpy of the 2 points, gives us roughly 83% of that heat is related to the sensible side of things. And 17% is moisture. 17% is moisture. So if your sensible heat ratio is 1, all sensible heat. If you've got 0, then you're strictly removing moisture. When you look at that. So the smaller your SHR is, the more moisture that you're pulling out, higher it is, the more heat that you're adding. Or removed, excuse me.
Hey, Jason, can I bug you to go back to the psychometric chart for this one? This is one thing I've had over the years, many facility operator people, when I've been talking to, maybe we find that they have air side economizer and they set it so that they only economize it, 50 degrees or lower, things like that. And they will say to me, well, but what if it's raining outside? It's 100% relative humidity. I can't bring in 50 degree, 100% relative air into my building. It's too humid. But if you see this process, because this is common, you start at 0.1, and this happens all the time during the summer, right? You're bringing outside air in.
Yep.
And if you see, you go across your cooling coil, you're at saturation anyway at 55%, right? 55 degrees.
You're
So
close enough to
you're
it.
doing it all the time.
Right.
So I have to explain that to them. So this makes it's kind of visual. You can see
Which
why
has
it's
led,
not a concern.
which has led some people though then also to look at enthalpy. Right, and how do I look at that economizer? Do I use an enthalpy economizer? Do I use a dry bulb economizer? Some people use them in tandem to try to optimize. Is it worth it, to your point, at the end of the day, to go through all of this in a control strategy to, for a couple odd days, when you look at bin data, right? Yeah, you're nearly saturated anyways.
Yeah.
You're nearly saturated anyways.
2 comments, one from Chris, to make sure to convert hours to minutes along the pounds to gallons.
Yep.
And
Yep.
then Charity says, you're doing great. What t-shirt are you wearing?
My sister's on the call. She's not in the HVAC world at all. Thank you, Charity. She's my moral support, so.
You're still awake. That's
She is. I put her to sleep.
Just set her alarm.
So thank you, Charity, I appreciate that. So back to the comment about converting, yep. So when you get to here, the 142 pound mass per hour, you will have to convert that 8.33 to convert that to gallons, and then you gotta convert that to minutes via the 60 factor. Good catch. Good thread, this Charity. I'm wearing Mikey's clothes. So my friend makes these the outfit that I'm wearing, so. Let's see, sensible heating and humidifying. Yeah, we're doing good. All right, so we got a clean suite. Again, a lot of this stuff is for my day-to-day work. So I've got a clean suite, 3,400 CFM of supply air, suite served by a once through. So anything I deliver, I'm exhausting out. I do that a lot for containment purposes, so I don't have to have HEPA filtration. So I'm delivering, whatever I deliver, I exhaust out the roof. I get my makeup air from the penthouse, which is served by makeup air system, and that's providing 60 degree Fahrenheit at 30% RH is my condition of the air in the penthouse to all the mechanical systems. And so to maintain my space, the air handler needs to deliver 70 at 40%. I do a lot of 72 degree Fahrenheit, what we maintain. We do a lot also with varying processes. I could have 20% RH requirement, or I could have no more than 60. So this is a common 70 at 40 that we try to maintain. It could be a little bit lower, but what's the total heat required from the heating coil? And then what is the humidifier load? We're using 212 degree steam, which has got a BTU, 1150 BTUs per pound mass. And we're gonna assume that there's no heat added from the steam. This is gonna be strictly just humidification. When we looked at that, right, we talked about adding humidity, you just go straight up on our dry bulb temperature. We don't change that.
What's that raised hinge like?
What's that?
Someone has their hand up.
Yeah.
That middle, there's that hand up. I don't know, between attendees and. Right there, they're doing it.
Lee's got his hand up.
Oh, allowed.
Yeah, here you go. There we go. Go ahead, Lee. Or just type it in the chat. The Q and
I think it
A.
might work better with Q&A.
Lee, hopefully I answered your question or. There. Sure, so we're gonna take the short road on this one. There we go. It's got going, again, our crude schematic, we've got our heating coil that we're gonna add heat to, and then downstream of that, we've got a humidifier. Gonna change that initial state as it goes across both devices. So we've got our points, we've got point 1, I got a number wrong, so point 3 is downstream of the humidifier there, my apologies. So we've got point 1, point 2, so I'm doing just strictly the sensible heat by the coil, sliding that all the way across, we're sliding that across to the right to that 70 degrees. And then we're gonna add humidity. We're gonna end up going directly vertical. And like I said, we assume that we're not adding any heat from the steam that we're atomizing in the airstream there. So I've got our entropies, we've got our humidity ratios of points 1 and 3 across final across both devices. So when we look at the short road of things, we're gonna, like I said, we're doing just sensible heat. We've got the 1.085 times our 3400 CFM, and then we're just adding, we've got the 10 degree delta T. We get a approximate size of 36,890 BTUs an hour that coil's gotta be sized for. Now, when we look at the moisture that we need to add to then maintain our humidity that we wanna deliver to the space to maintain it, we're taking that 4.5 times our 12,000 CFM, take that delta of the humidity ratios. Looks like I got another typo, and nobody caught that one. But that's supposed to be 1, not 21. And then we're divided by that 7,000 factor. So again, we come up with, I think this is wrong. It's a copy paste there. Anybody, let's see what do we got here? I don't think that's right. On second glance.
Starting off at 20, you're going up to 23 and a half.
Yep, so we're 44 minus 22 point, excuse me, 23.5 gives us the change in of 20.5, divide that by 7,000. And then we're gonna multiply that by 12,000. And then the 4.5. 158. Copy paste there, my apologies.
Where do you get the 12,000 again?
12,000 is our airflow, 12,000 CFM of our unit.
Oh, this wasn't 12,000.
No, it's not, totally.
3,400.
3,400. Total copy paste job. Sorry about that.
That'd be a really big humidifier.
Yeah, that, so 4.5 times the, what did I say, 3,400?
Yep.
Times 20.5, divided by the 7,000. I should be at 44.8 is what I got. So my apologies for that.
Jason, your quality control team here apologizes for not mentioning.
No, it's all. The good thing is I'm recognizing that I've got an error,
Yeah,
Yeah.
that's a good point.
right? I mean, hey. So my apologies, 44.8. So it's not that big of a humidifier. You'd love to sell me that humidifier. So, but it, a much simpler way, right? I mean, you don't have to go through the whole, I mean, the long road is a long road. And there are times that it makes sense to take the short path, so.
Are the engineers in here, when you do a humidifier, those wands are really hot, right? It's boiling water. Do you guys take into account?
It can be insulated. Right, we're gonna, you can have an insulated, dispersion tubes, right?
Most of them are insulated.
It depends on the application.
Okay.
I mean, if it's gonna be critical, we'll definitely make sure that's accounted for.
'Cause that can be like 3 or 4 degrees. It's a lot of BTUs.
And I'm sure there's a way for you to do that.
If there was only a way. Right now, it's just a mystery.
Totally. You got the diamond head, another good one.
I've asked 3 or 4 questions, not one gummy. Man, didn't you with the gummy?
Yeah.
Thanks, Jason.
You are welcome, sir. My apologies. Okay, anyone want coleslaw? Oh, dude, we have a formally informal process of going through this. All right, so we've looked at a lot of individual processes. I guess now let's try to wrap our arms around a little bit bigger scenario. And this will be two-folded. I'm gonna make an assumption in the first one, and then kind of to your point about heat that gets added, we'll go back to that original and we'll see what impacts it has overall. So I've got, we're gonna look at find the overall airflow. So I'm not giving you the airflow rate. I want you to find out what you need in order to maintain your space. And then we're gonna look at the actual conditions of that supply air that we are gonna deliver to our space. So I've got a constant volume, single zone air handler serving a warehouse. Warehouse load has a total load of 100,000 BTUs an hour and a sensible load of 75,000 BTUs an hour. Return air from the space is 77 degrees and with a relative humidity of 45%. Outdoor air conditions, fairly common, 95 and 75, dry bulb, wet bulb respectively. And we've got, we're bringing in 750 CFM of outdoor air. So what are the airflow requirements of the air handler? This will be the total supply air. What are our mixed air conditions? And then what's that cooling load across the coil? For this first part, we're gonna assume 0 heat gains from the fans. And we're gonna look at a 20-degree differential across our supply air, or excuse me, the return air and our supply air from the discharge of the coil. And then we're assuming that we got no exhaust, we're only relieving. So we're taking what we deliver, we're bringing back, we relieve and bring in. A little bit better diagram, thank you, Blue Bean. And so we got a couple points, we got point 0 is our outdoor air. Point 1 is going to be the mixed air condition and what we're looking for. We're looking for Q for our coil. And we've got, we're looking for our discharge air temperatures, conditions, I should say. I've given you the load of the warehouse, so total load and sensible load. And so that we can look at find our sensible heat ratio there. And then we got point 3, which is our return air coming back from the space. 5 is negligible, that's just the relief. And then 4 is what we're bringing back to mix with our outdoor air. So with that, we're gonna plot a couple points. So 0 and 3, 0 being the outdoor air. And then point 3, which was our return air, that we're bringing back from the space, correct? So we've got those 2 points plotted. We're going to go ahead and find the sensible heat ratio. Well, we know that, right? 75 over 100. So that gives us a sensible heat ratio of 0.75. So how are we gonna find this? So what we're gonna do is to that middle point that you guys have at 75 and 50, mine's a little different. But you're gonna draw a line from that point that's in the middle of your site chart over to the right-hand side to 70%, was my heat ratio.
75.
75, so I did 70. We're adapting as we go.
That's how you interpreted the chart.
So it's 70. So it's 70, it changed, but I know why it did that. I know why I did that. So we're gonna go 70. We'll change that to 70, okay? So we go back, we connect the two, the middle dot to the far right. Now you're gonna take that parallel line and you're gonna take that and you're gonna go from point 3 back to the line of saturation, 100% saturation. So now, like I said, anywhere on this line, going from point three all the way back here, you can deliver air at anywhere that's on this line. So I assumed that 20-degree delta T, so that's putting us right here. I can assume a 15 or a 10 degree, right? But the lower the delta T, the more CFM, the higher the CFM we need to maintain our space. The lower that temperature on the left-hand side, if I wanted to go even lower down, if I wanted to go to 50 or 51, I need less air. Right, so I'm assumed a 20-degree delta T. So I put us right at that 58, 57 degrees, because we're at 77, so we took 22. And I know where that condition is gonna be for the enthalpy and everything else about that point, because it's on this line, our sensible heat ratio line, 70%. Okay? That make sense to everybody? How we can find that point? So by making the assumption of that discharge or the temperature of 57, we can fall anywhere, we can go up to that line, and now we know every condition then, so that we can carry on. So with that then, we've got this is our mass balance, our energy balance. I've neglected the moisture. I don't have that factor in here, right, in terms of cooling, dehumidifying. I've left that small, the energy related to the condensate. That's left out of this. So find our mass flow rate from manipulating our energy balance. So we've got 100,000 BTUs, that's our total, that's the total energy. We're gonna divide that by our difference in our enthalpies from point 2 to point 3. So we knew this because we made an assumption of 57 degrees, so we can perform this calculation. So with that, I get 13,514 pound mass per hour. So when we convert this over to the volumetric flow rate, to find the total CFM that we need to maintain our conditions, we're gonna need roughly 3,000 CFM. Again, we've corrected this with 13.19, that's our specific volume. And that's of 0.2, that's from the state 0.2. So now we need 3,000 CFM, right? So in this scenario here, we've got our mixed air, we wanna find out those conditions. And so 0.0 is our outdoor air, and we're adding 0.4. Right? I think I didn't give the schematic again. So with this, we know the mass flow rate of our outdoor air. Convert this over to the actual mass flow rate, because we pulled the 14.29 off the chart for the outdoor, based on the outdoor conditions. So we're at 3149. So with that, we can do some simple math to figure out what air is recirculated, is coming back, right? Because we knew what our total mass flow rate was. We know what our outdoor air flow rate, mass flow rate. So now we've got 10,365 pound mass per hour being recirculated at the unit. Which leads us to how we can find that, what's that final condition of the mixed air, which is 0.4, or the state 0.4. So I saved this with converting this formula, the humidity ratio 1, equaling this. There's 3 other formulas that are combined into this. So this is I've simplified it for us. So state 0.4, let me go back again, pardon me. So state 0.4, we know that, people online, pardon me. So we're not adding any moisture, we're not adding any heat from this fan, right? So the moisture humidity ratio within 0.3 has got to equal 0.4, because we haven't done anything to that air, okay? So that's constant, so 3 equals 4, right? And we're looking at 0, difference between 0 and 4. Bear with me. So with that, state 0.4 is 74 grains, because that equals what 0.3 is. So we're gonna add to that the ratio of the mass flow rate of 1, which is the combined, 13.4, that's what we've got. Take that, divide it, we're dividing the outdoor air by the total, excuse me. And then multiply that by the difference in the grains, that humidity ratio, which is 0 and 4. And so we end up with a 79.8 grains per pound. So when we look at that now, so we went through, we had our points from 0 to 3. We found out our dry bulb temperature, right? So that goes up to this point, and now we come back to right here. Well, pardon me, let me go back. We knew where this was. We just found it, so we came straight across. We hit
W1 is, what is that again?
W1, that
Humidity
is,
ratio?
that's the humidity ratio of
75.
our mixed air. That's
Oh, mixed.
mixed air, after we've combined the recirc air with the outdoor air. So knowing what, we just found this, we go horizontal across, we hit from 0 to 3, and we come down and we find our new dry bulb temperature of our mixed air. We haven't added anything in terms of humidity, so we can come straight across. And then drop straight down, constant temperature. So now we have 88.5 or 85.1, excuse me, 68.6, 0.8, excuse me, for the wet bulb. So we've now defined our mixed air condition. That's what our coil is gonna see. Right? That's coming into our coil now. So with that, we've determined our enthalpy. And with that, now we can find out that total and sensible load of the coil. Our schematic again, for reference. So when we find the capacity that's required for the coil, we're gonna look at the difference of our enthalpies of between 0.1 and 0.2. But we know that the mass flow rate of 1 and 2 are the same. We haven't taken anything out before it goes across the coil. So we can say our mass flow rate times our difference in enthalpy of 0.1 and 0.2 gives us 142,000, roughly 12 tons of cooling. Again, we haven't added any sensible heat from the fans, right? We've neglected that for this part. Does all this make sense? Okay. So we want to find the sensible heat ratio. I was wrong the first time, we went with 0.7. But now we're gonna find this one. This is gonna be the sensible heat ratio of the coil. We have the sensible heat ratio of the space. We're gonna look at the coil now. That coil is gonna have a differing sensible heat ratio. So we've plotted, all we're gonna do now is we're gonna go from 0.1 to 0.2. We're gonna draw a straight line. And what we're gonna do, we're gonna take that line and we're gonna go to my center point was here. And I transcribed that all the way back to the left and right hand side of the psycho chart. And so when I did that, I got a sensible heat ratio of, did I write it on there? I didn't. It looks like I'm about 65 or 66% on the sensible heat ratio after so this line, my purple line and the red dotted line are parallel. So I just took this line and added it to that SHR point and pulled that all the way across to give us the coil sensible heat ratio. So with that 0.652, very explicit, right? Again, it's interpretation. So to find the overall sensible load of that coil, take that sensible heat ratio times the total energy of the coil, the total, and we get 92,500 BTUs an hour. And when simple subtraction, and we get roughly 49,000 for the latent load.
So that's a hard coil to get, isn't it?
That much of a latent load?
Yeah.
I mean, you start adding fins, you add rows of coils, right? You can do I've hated doing it, but I've seen like 10-row coils with 10 fins per inch. How do you ever clean the darn thing? You know, like, but in, I guess probably the last one was like in a healthcare application where it was a subcooling unit is what we technically called it. Because we were trying to reach a dew point in the scenario that I'm actual application that I had, with that, but it's a big coil, I mean, it's a big coil.
If you end up with, I mean, does it happen where you size the coil for humidity, but you end up overcooling?
You can, yeah, I mean, all of this just helps us to be well informed of what we're gonna be able to do, what we need to do with a particular coil. And you can also then verify with what you have in existing condition, right? If you know what your load on the coil is, or you can work backwards in all this too to solve problems. Not necessarily getting to this point, but you could start from this point and work your way all the way
You know,
back as well.
conveniently, our next class is about coils, so there you go.
There you
What a
go.
great lead-in. Thanks, Jason.
Yeah, you bet. Happy to help, happy to help. So the final outcome of our trip, this was all the work that we did, right, on that psych chart. A lot that goes into it, but it gets us to what we need and where we have to go. And it's not always a short road to get us there. But let's take into account the heat from those fans. Right, so you add heat by fans, what I typically see in my bigger air handlers, I can see anywhere from 2 to 4 degrees. And this is from fan walls, fan arrays, whatever you wanna call them, they're dumping heat into the airstream. So we're gonna look at fans and,
Just the motor, right?
so we're gonna look at motors in the airstream for this example. Yeah, I just had a typo here, that's my problem, it was always 70% is what I wanted. So when we plot everything, again, it's the same, 0 and 3 are the same, we haven't changed anything. So that's easy peasy. Go back and find our sensible heat ratio like we did, that was, we did the 70%, right, so that came back over to here. So all of that works out, still that 20-degree delta T. So we come up with the same airflow rates. Everybody remembers my numbers, right? They're all the same. We make it through that. But now we're adding sensible heat as we, from the return fan and the supply fan. So this is looking at motor inside the airstream. We've got the sensible heat gonna be equal to this factor C5 times the brake horsepower divided by the over motor efficiency. So my supply fan, I've got a brake horsepower of 2.2 and a motor efficiency of 90%. My return fan, we got a brake horsepower of 0.82 and 90%. So we can now then figure out what heat's added sensibly from each of these. So we get about 2 degrees total from our supply fan heat. And so I use that formula, but then I use the shortcut route of the 1.085 CFM times delta T, and that delta T is what we solve for to get our roughly 2 degrees Fahrenheit from the supply fan. And likewise with the return fan, we get just about a degree of rise. So I'm gonna use 2 and 1 for carrying on this analysis. And so when we add these points, what we're gonna do here is, so point 1 prime, this is from our supply fan. So we're gonna move over to the left those 2 degrees horizontally across the constant humidity ratio, because it's just sensible. And then likewise for the change in the 0.4, this is the recirc air, right? We've added 1 degree from that return fan. So now we're making a connection between 0 and 4 versus previously it was 0.3, right? Because we weren't adding any heat. So we changed our dynamics a little bit. And we're also now looking at the 1 prime versus 0.2. So our mixed air balance, again, stays the same. Our recirculated air all stays the same. And our humidity ratio all stays the same. So with that, our W1, we just come straight across. Now we've got a new line here, right? Before it was from 0 to 3, we've shifted over a little, so it's changed our T1 that we're seeing within the mixed air conditions. So that point is 86 degrees and 69.2 for a wet bulb. So that's what we've got for point 1. what we wanna do now is, we're gonna look at, instead of 1 to 2, we're going to 1 to 1 prime to look at our coil capacity. Because now we've added heat in 2 places. So to get this, total coil, energy balance, we'll look at this, we've got our schematic again. So we've got the same mass flow rate, but now we've got differing enthalpies. You know, the enthalpy prime, 1 prime was different than 2, a little bit lower. So that little bit of change between those points, we are now looking at 12.7 tons versus we were shortly of 12 before. So we've added like a ton of cooling, roughly 10% to our, just by adding the heat from the fans, we've changed the needs of our coil. So if we don't take that into account, I mean, a ton of cooling is a ton of cooling, you know, 12,000 BTUs, right? I mean, that, on a design day, you could be up the creek without a paddle. Hopefully not, but, so there is a difference. So we wanna make sure we account for it, in the analysis. So at the end of the day, we're gonna go back and see what now our sensible heat ratio is, right? So that we're gonna take from 1 to 1 prime line, and we're gonna then transcribe that back over to the sensible heat ratio. And again, we're at about 66.8 or 0.668. We come up with a sensible load of about just over 102,000 BTUs an hour, and we're looking at roughly 51,000 BTUs of latent load. And all we did was add heat from the fans. And this was relatively small, like I said, sometimes I can see anywhere from 2 to 4 degrees, depending on the quantities and the size of the fans.
Just made it worse.
Correct. The coil, correct.
Yeah, you
There's a
basically
higher load on the coil now.
need a lower discharge air temperature off your coil if you want the same supply air temperature.
Right, so we assumed, right, we stayed on, we're still here, right, this was our point, we assumed this, but we had to move over sensibly. And so now the load of the coil is no longer from 0.1 to 0.2, it's gotta take into account the extra sensible.
I would have thought the ratio would have gotten better because you need more sensible cooling, right? You added made it 3 degrees warmer.
Mhm.
Your humidity load or the latent load should be the same,
But you still move on the chart though, right?
right?
We're still moving from our original point of not having any heat. We've got to move over, which does change in that sense where we are, the enthalpy of that air once it's all combined. Cause that 1 prime was mixed,
Right.
that's all mixed air at that point. So there is a slight variation in that. Am I correct? Do I need to be corrected on that?
Back to your original sensible heat ratio.
I think it has increased, because I think it was
So it will-
0.65.
It was 665. Or did I pass it? No, I didn't.
Maybe.
I mean, the coil sensible heat ratio is changing.
Yes, the coil, not the space.
doesn't-
It's the coil load changes, not the sensible, not the,
I thought it was like, it's like 50 to 100.
There it is.
Yeah,
so
0.65.
0.65, this is the
So I
coil.
got it.
Yeah, so it did.
So it improved.
it did improve. S to T ratio improved. Yeah, okay.
Sorry about this for the folks online.
It's a psychedelic.
A little faster. Maybe we had too much too fast. See, I told you we'd have some fun. I say this frequently to myself, what a long strange trip it's been. It certainly has, just life in general is, but this was a fitting photo, right? We're just kind of gazing off into the unknown. Like I said, it's an esoteric subject, both of them. Not a lot of people know anything about it, very few understand it, so hopefully garnered something out of the conversation today. But it has been a long, strange trip. So what do we gain from this particular experience? Psychometrics is wrapped up in everything that we do day to day when we're dealing with air. It's there. It's straight up there. And sometimes we get shown the light. Some places when we look at it right, it's all about perspective. I learned something, like I said, from when I was preparing this, that lines of enthalpy are not always parallel to each other. So I wouldn't have necessarily found that out at this point until further evaluation of years possibly, but putting this together, I was able to learn something as well. So I think it's all a matter of perspective and how we're shown. And there's truly more than meets the eye with the psychometric chart, right? It's not just a graphic that, you know, some old geezer put together and dropped a bunch of stuff on. There's actual meaning behind it. It's a very useful tool. So make use of all the tools that we have, right? Like we've got a toolbox as engineers, contractors, in this HVAC world. Make sure you open that box up to see what's there, add new tools as you go along. If you see that something doesn't work, chuck it. But usually there's a lot of tools in our box. So couple things, these are on the charts. So these are just some simple little tools to use, simple equations. ASHRAE, like I said, they're useful, very useful. Manufacturers, obviously TempMaster's got a psych chart out, but people can help you with humidification, dehumidification, evaporative cooling. There are online psych charts, like I said. And when in doubt, take the long way home. You know, that won't lead you astray. When you get confused, just listen to the music playing. So all my references, to be politically and make sure I haven't stolen anything, these are all my references. That's it. So.
So a couple of quick announcements for those here. We've got lunch ready to go. You should have received your first blog post about our May Road show, which is going to be featuring a lot of hands-on stuff. So one is a live system effect demonstration with Lauren Cook. So we're gonna take a fan, we're gonna put different fittings on it, and oftentimes in the field people go, "Oh, your fan's not working right." Well, take the same fan, put different fittings on it, the performance changes, and you go, "Well, wait a minute, it was the same fan, wasn't it?" So this is a good hands-on teaching, learning kind of a thing with Brent Fullerton from Lauren Cook. We're gonna have another one with Ruskin about properly installing life safety dampers and what happens when you can't get it to fit. And then the third one is we will have an electric and gas-fired humidifier, a couple other pieces of equipment with Neptronic, and show you like how important it is to service that stuff. So there's a very hands-on, both engineer-friendly as in like, hey, it's different than the lines on your Revit model. And for contractors where you're like, that'll be fine, I'll just put it in that way, you can see what happens when you don't plan ahead. So that's May, 13th, 14th, 15th in Milwaukee, Madison, and Green Bay. So registration's open, hope to see you guys there. So thanks a lot, everybody. All right.
Thanks, everybody.